we're going to start looking at the basics of hypothesis testing. And you guys know that you can go and print this out from Blackboard. You can pause the video to fill in the blanks. You can go to the textbook to read up or look at the videos by the author, whatever other videos that I've made. I will also be making videos where I'm working through examples. So all of the videos that follow this presentation will be made under the assumption that you have already figured out this video. Like you've already looked at it, you've looked at the book, you've figured out the definitions, and I can proceed thinking under the assumption that you know this stuff. So we have an example that we're going to use as the basis for understanding the basics of hypothesis testing, and then we'll look at how we can extend that to other types of tests. So this test says that we're going to assume that 100 babies are born to 100 couples treated with a special gender selection method, and it's supposed to make girls more likely. Then there's a sample. We collect some data. We observe 58 girls and 100 babies. We test the claim that this method has resulted in a proportion of girls that is greater than the 50% we would normally expect without treatment. We're being told down at the bottom here that we should assume that the normal distribution does apply here. We can use it to approximate our binomial distribution. So that last line I've discussed previously about, I think in 7.2 I explained that we can use the binomial distribution, or we can use the normal distribution to approximate a binomial distribution if certain conditions are true. And we learned about those requirements when we went through section 7.2, which was about confidence intervals of population proportions. So I'm not going to take time to go over that now, but you can look back in 7.2, which also might point you back even further to another section of the book. But we're going, this last line here, why it means something to us now without even having to know exactly what it means. It's just letting us know that we can assume the binomial distribution. We're not going to take time we're going to assume that it works. We're not going to take time to check the assumptions. All right, then we have hypothesis testing steps. Now these steps, I'm not going to spend a lot of time here because I have summarized all this stuff for you into that form, what I call the HTG form, which is the hypothesis testing guide form, which I give you on tests and is worth a very large amount of the points that will be available for the test. So you want to make sure that you learn how to follow through that form. We have definitions. A hypothesis is a claim. A hypothesis test is the procedure for testing that claim, which we're going to be learning. We have the null hypothesis, which is denoted with a subscript of 0, h sub 0. It is the default assumption that we are trying to reject so that we can support an alternative, which hopefully will be our claim. We want to word our claim so that it falls under the alternative. The alternative hypothesis is going to be symbolized by h sub 1. Sometimes it's symbolized as h sub a, depending on the textbook, but for us, we're going to be using h sub 1. And this tells us that our alternative always is different than the null hypothesis. The symbolic form of the alternative must be one of these. Notice that none of these options contain equality. Sometimes the alternative hypothesis is the same as the claim, and sometimes it's the complement of the claim. The null hypothesis will always have the equal sign. That's for certain, no matter what. So then the only thing that changes is the symbol of the alternative hypothesis, meaning the only thing that will differ from example to example is the symbol of the alternative hypothesis. And it can't contain equality, so it has to be one of these options. And so if the claim is stated so that you can state it symbolically without any equivalence, then your claim is the alternative hypothesis. However, if there's equivalence in your claim, then it is covered by the null hypothesis, and since your claim can't be partially in both hypotheses, so then your alternative would have to be the complement of the claim. So for instance, if your claim uses the equal sign, then your alternative will be the not equal sign. If your claim uses this symbol, then your alternative will be strictly greater. And if this symbol, then strictly less. Also, what's really important is that we look at the sign of our alternative hypothesis to determine whether we have a left-tailed test, a right-tailed test, or a two-tailed test. So let's go back over to the PowerPoints because more of this is illustrated as we go forward here. Then we need to define a few other things. We've talked about a significance level before, and now we've talked about it in a very vague way when we were in Chapter 7. We were learning about how to do interval estimates of proportions and means, and we talked about how you have a confidence level, and then the confidence level has a corresponding significance level. So for instance, if you have a 95% confidence level, then your significance level would be 0.05, or in other words 5%, but we always put the alpha as a decimal. If you have 99% confidence, that corresponds to a significance of 0.01. And if you have a 90% confidence, that corresponds to a significance of 0.10. And so that we see again in this section, but now we're going to talk about what it actually, what it means. What is a significance level? What does it mean? It is the probability that the test statistic will fall into the critical region, right? So this is the region under the bell curve, which we consider to be the rejection region, which allows us to reject a null hypothesis. But we could reject a true null hypothesis by mistake. So we want to try to limit the probability that we're going to make that mistake, and the significance level represents the likelihood that we would make that error. So the critical value is attached to the significance level. So whereas alpha, the significance level, represents a probability and therefore an area under the bell curve, the critical value is actually a boundary, and it's attached to that critical region. And alpha also can be referred to as the significance level, the probability of a type 1 error, the critical region, the rejection region, and then you have the critical value boundary on that. Then we have something called a test statistic. It is a value used in making a decision about the null hypothesis, and it is found by converting the sample statistic. So here's the thing. You are trying to determine something about the population by using sample data. So you make a claim about the population, but then you use a sample to test that claim. Whatever the sample statistic is, you will then need to turn it into a standardized value under the assumption that the null hypothesis is true, and then you'll compare that critical value with the test statistic. So let me show you another illustration that relates to this. We have two sets of areas paired with boundaries. One is the area that represents the probability of making a type 1 error, and then the boundary attached to that is a critical value. We also have a pair that comes from the data, and we use a formula to create a test statistic that can be compared with the critical value. So the critical value will be a z-score, a t-score, so your test statistic will need to be a z-score or a t-score as well in order for you to be able to compare them. So we take our sample statistic, we turn it into a z-score or t-score, and then we compare it with that critical value. Also, we can use that boundary to figure out what the area is that's attached to it. So there's two ways of making a decision. You can compare areas with areas. So these are both areas, your alpha, which is your significance level, and your p-value, which is the probability area associated with your test statistic. You can compare critical values with the test statistic. So you can compare area with area. You can compare boundary with boundary. And no matter which one you choose to do, you will arrive at the same decision. They are equivalent methods. Okay, so back up to where we were, talking about a test statistic. So what we said is that we're assuming that the null hypothesis is true, which just means that when we use our test statistic formula, we will plug the claimed value in the null hypothesis will be plugged into the formula in place of the population parameter. So here are the test statistic formulas that are summarized in our reference packet. And this test statistic formula right here, you can see the sample statistic symbol p hat and the population parameter symbol for the population proportion p, sample mean x bar, population mean mu, and then you also see the sample standard deviation s and the sample standard the population standard deviation sigma. So this summarizes how we know which formula to use. We use always z-scores for p, and this is the one test statistic if you're doing a claim about a proportion. There's only one test statistic formula to use. For the mean, there's the t distribution if you don't know the true sigma, and there's the mean with the z distribution if you do know the true population standard deviation. And almost all of the time, we will be using the t distribution because we usually don't know what the true population standard deviation is in practice. So it kind of boils down to, if we're doing a claim about a proportion, a percentage, then we will use this formula, and if we're doing a claim about a mean, we will be using this formula. And when we use this formula, we're going to be taking our test statistic that comes from the sample data, we'll be plugging in the claimed value that's in the null hypothesis for the parameter, and then we will figure out this calculation so that we have a z-score we can compare with the critical value. Okay, so that brings us to the next point, which is the types of tails you can have for a test, two left and right. Whereas confidence intervals are always two-tailed. There was no choice with confidence intervals. We always split alpha up into two tails, and we will continue to do so because whenever we do hypothesis tests, we can also do a corresponding confidence interval, and no matter what kind of tails we have for our hypothesis test, if we do a corresponding confidence interval, we will use two tails for that confidence interval, even if we have a single tail for the hypothesis test. But we want to start to know how to tell if our hypothesis test will be two-tailed, left-tailed, or right-tailed, and it's very easy. Null hypothesis always uses the equal sign. The alternative has to either use this symbol, or that symbol. No equivalence every time. So we have two-tailed tests, left-tailed tests, and right-tailed tests. Then we have something called the p-value, which is attached to your test statistic. The test statistic, we figure that out using the sample statistic, turning it into a z-score, t-score with one of these formulas. Then, based on whether we have a left-tailed test, a two-tailed test, or a right-tailed test, we'll be looking at a certain side. So our test statistic might be on the right with the critical value on the right, or on the left with the critical value on the left. It could be, if you have a left-tailed test, your test statistic is definitely going to end up on the left, or rather it should if we've done everything right, unless it's a weird example. And if you have a right-tailed test, your critical value will be on the right, and your test statistic will end up being on the right as well. And then the p-value will be attached to that. So the p-value is connected to the test statistic. The critical region is attached to the critical value. Right? So I keep referring to the green pair and the red pair. That's a reference back to this. Remember we said there's a pair which includes the alpha and the critical value. So the critical region and the critical value. We also have a test statistic and a p-value. And the order procedure of a hypothesis test, you'll get the alpha, the significance level, will be given in the problem. You'll use that area to find the attached boundary. Then you'll take your sample statistic and standardize it to get a boundary. that's associated with your sample, and then you'll use that boundary to find the area attached to it. And that way you can make a comparison. And when the whole test is finished, it'll look something like this, where your critical region is bounded by the critical value, and then you've got some test statistic either inside or outside of the critical region, and then there's actually this is not sufficient to me. I would like to see this a little better. Let me pause for a moment so I can give you. Okay, so this is what I wanted to show you, that your test statistic, when you illustrate it, you'll use the asterisk. Then you'll draw a boundary up to the curve. So we've done something like this before with chapter 6. And then just like the critical value, which has the red boundary line there, has the red area alpha attached to it, shaded region to its right, your p-value, the p stands for probability, the probability of the test statistic being this extreme, is the shaded region to the right of that. And so you'll see that the p-value is completely covering the critical value. The p-value is actually larger than the red region. And so that means that the critical value is more extreme than the test statistic is, which means this is not a significant result. So we will not reject the null hypothesis in this case. You can break these things down into smaller steps, but there are 5 main phases for a hypothesis test. You'll start by determining what the null hypothesis is and what the alternative hypothesis is. And then using the alternative hypothesis, you'll know the tail type, whether it's left, right, or two-tailed. Next, you'll use the given alpha to find the critical value boundary and illustrate that under your curve. So that would be the red couple, the red region. And then you'll use your test statistic or your sample statistic. You'll use the formula to get it to be standardized, and then you'll use that to find your p-value area. So that would be the green couple, and you can illustrate that under your curve. Then you'll be ready to make a decision whether to reject the null hypothesis. So if your test statistic falls before the critical value, closer to the mean, if your test statistic is closer to the mean, that means you will fail to reject the null hypothesis. If your test statistic is beyond the critical value and farther into the tail, then you will reject the null hypothesis, because then your sample is more extreme than the critical value set by your significance level. And then another way of saying that is that if your p-value is smaller than your alpha, you will reject the null hypothesis. And so there's a rhyme to help remember that. If the p-value is low, the null must go. Then, based on whether or not you reject the null hypothesis, you will then be able to turn that into a conclusion about your claim. And your claim is sometimes contained in the null hypothesis, and sometimes it's contained in the alternative hypothesis, which brings us to a flow chart of how to word the final conclusion. We're going to determine whether the claim contains the condition of equality, because if it does, then it'll be in the null hypothesis. If it's in the null hypothesis and we reject the null hypothesis, then we are in effect also rejecting the claim. If your claim is in the null hypothesis but we fail to reject it, then we are failing to reject the claim. And then there's the other possibility, going back to the first decision. If the claim does not contain equality, then it becomes the alternative hypothesis. So when we reject the null hypothesis, we would be supporting the alternative. And if we do not reject the null hypothesis, then we will say there is not sufficient evidence to support our alternative. Right, so let me pause here and see. Okay, now a quick word about the importance of stating your decision correctly about the null hypothesis. Remember that we are always deciding whether or not to reject the null hypothesis. And we don't discuss the claim there, because sometimes the claim is in the null and sometimes it isn't. So when we're discussing whether to reject the null hypothesis, we have to be very specific with our choice of words. Some texts use accept the null hypothesis, so you may see this in other textbooks, usually older textbooks, but it is not correct. So just beware of that. If a tutor or anyone is trying to tell you that failure to reject the null hypothesis is equivalent to accepting the null hypothesis, that is completely wrong thinking. So just beware of that. We are not proving the null hypothesis. That's not what this is about. We're only looking to see if we can support an alternative to the null hypothesis. So fail to reject says more correctly that the available evidence is not strong enough to warrant rejection of the null hypothesis. Okay, so it may seem like just semantics, but it actually is relevant. Then this little chart shows us type 1 error and type 2 error. So if you decide to reject the null hypothesis and the null hypothesis is actually true, that would be a mistake called a type 1 error. However, if you're rejecting the null hypothesis and the null hypothesis was false, that's a correct decision. Now we typically don't know if we're making a type 1 error or not. That's the whole point. This is all about probabilities, likelihoods. So we're just guessing, really. Educated guess, guesses based on likelihood, probability. But the reason it's important is because we're always trying to minimize that type of error by controlling alpha. And if we fail to reject the null hypothesis when the null hypothesis is true, that would be good. We don't want to throw out a true null hypothesis. However, if the null hypothesis is false and we fail to reject it, then that's another type of error called type 2 error, and we refer to beta as the probability of making a type 2 error, and we also refer to that as the power of the test. Then we have this example here, which is the same example that was presented at the beginning of the lesson, and we're just going to look at specifying what a type 1 error would be and what a type 2 error would be. So in this case, where we say we are assuming that conducting a hypothesis test of the claim that a method of gender selection increases the likelihood of a baby girl so that the probability of a baby girl is greater than 0.5, if the null hypothesis is true and the XOR method really is not increasing the likelihood of having a girl, but we choose to reject it because our test leads us to that conclusion, that would be a type 1 error. So a type 1 error in this scenario would be rejecting a true null hypothesis, which would conclude the probability of having a girl is greater than 50% when in reality it is not. Right? So then in that case, our sample data would have misled us. It doesn't mean we messed up in our procedure, but that our sample may have been faulty. B, a type 2 error would be the mistake of failing to reject a false null hypothesis. So if the null hypothesis actually is false and the method is actually effective, but we fail to reject the null hypothesis, so we miss the fact that it's an effective method, there is no evidence to conclude the probability of having a girl is greater than 50%. If we conclude that, our data would have misled us again. We can test claims about population parameters using p-values and test statistics and confidence intervals. Now, confidence intervals is actually a separate method that we can run a confidence interval alongside a hypothesis test. Hypothesis test is comparing p-values with alphas, or test statistics with critical values, and that they're equivalent methods. Those two first ones fall under the heading of a formal hypothesis test, just different perspectives of looking at the results. But 3 confidence intervals, that's different, and it can sometimes disagree with your hypothesis test, but it's useful to do both because then we have more understanding of what the data is telling us. The level of confidence of the confidence interval sometimes differs from the confidence level of the hypothesis test. I've alluded to this in the past when I introduced confidence intervals and telling you that they're always two-tailed, but our hypothesis test, which we will get to in the future, and here we are now, will sometimes differ. But we will always use confidence intervals two-tailed no matter what. So if the hypothesis is two-tailed, of course the confidence interval is two-tailed because it always is. If the hypothesis test is one-tailed, it doesn't matter for the confidence interval. The confidence interval will remain two-tailed. And because of that, we end up with a result where the confidence level will be 1 minus alpha if the hypothesis test is two-tailed, and that's what we're used to seeing. Remember, if we had a confidence level of 90%, then alpha was 1 minus that 10%, 0.10, and vice versa. If we have an alpha that's 0.10, then our confidence level is 1 minus 1.0. So it would be 90% confidence. So that's the first case is what we're accustomed to. Now in the second case, if the hypothesis test is single-tailed and the alpha, let's say the alpha given is 0.10, our confidence level for the interval estimate will not be what we would expect. It will not be the 90% that we are accustomed to. We would actually end up with 1 minus twice the alpha, and I will give an illustration of why, but there is a link here that you can go to if you want to read up on this, if you're really interested in understanding it. But this link mainly explains why we always stick with a two-tailed confidence level even when we have a single-tailed hypothesis test. But I won't go into the details. I'm trying to keep it simple, more focused on procedure. So the illustration of why this is true, I'll show you here. So I'm writing with my mouse. I apologize, this is not going to be the best looking drawings here. But let's say we have a hypothesis test that is two-tailed and alpha is split up on each side. So the area here is alpha half, right? Our confidence interval, which is always two-tailed, sorry, this is just really hard with a mouse, is going to be also two-tailed, and therefore it makes sense that since alpha half is what we always have in each tail for confidence interval, these will match automatically. Okay, but the second case, I'm going to try drawing with my finger and see if that helps. It's a little better. If you have a single-tailed, let's say it's right-tailed for the hypothesis test. So you have this critical value over here, and your alpha is fully on one side. Your alpha here will have to be split up for the confidence interval, because again, the confidence interval is always two-tailed, so the alpha will have to be split up. So let's say the alpha was 0.10 here. This has to be 0.10 also because the two right tails have to be the same amount. But since we know that the confidence interval has to have two tails, we actually end up having to double that 0.10. And so we end up with a significance level of 0.2 and therefore a confidence level of 80% rather than 90%. Okay, so the key is that the alphas will be different, right? Because the alpha for this case would be the total of the two tails, which would be 0.20, where the alpha for the hypothesis test was just 0.10 and it was all on one side. Okay, so that is the summary of the PowerPoint. It's really just a quick overview of what's in the textbook, so I recommend reading through the textbook. If any of that seemed to hop around a little too much, you can go back through the book and kind of try to make sense out of it if you feel you need to. But you might at this point be able to start looking at my videos of actual examples that I'm going to do. And I also want to remind you of one other thing, and that is the hypothesis testing guide, which is worth, as it says right here, 18 points. So if I give you this on the test, and I will give it to you on the test, it's not even a question. As you're filling in each of these boxes, you are gaining points, and you can earn 18 points if you know how to do this. And if you don't know how to do it, then the highest grade you can expect on the test is an 82%, and that is if you are 100% on everything else, which is, you know, unlikely in most cases. So you're eliminating almost 20%, almost a fifth of your entire grade by not knowing how to do this. And every single time we do this test, I have quite a few students who completely skip doing this. You cannot avoid doing this. You will not pass. So it's absolutely crucial that you spend some time understanding this, and if you can't understand it, you've got to bring it up to me so that I can help you clarify. And as with everything else, it's all about practice. So I went over, within the PowerPoint, we did go over how to fill in these boxes, how to determine the tails, how to know which distribution we're going to use for our test statistic formula and our critical values. The significance level, what the area and the tails will be, what the critical value is, which we find based on alpha, test statistic based on the sample data, the p-value based on the test statistic, how to illustrate the curve, how to make a decision about whether or not to reject the null hypothesis, and then the conclusion of the claim. We also went over how to understand how the confidence interval can have a different confidence than you expect. Remember to draw the sketch of the curve, and whatever your alpha was up here, if this is two-tailed, if your test is two-tailed, then everything is a match automatically. So your alpha will be the same as your original hypothesis test. However, if your hypothesis test up in this part is single-tailed, either right-tailed or left-tailed, then you have to double your alpha down here. Your alpha has to be twice as big as the one up here if your hypothesis test is single-tailed. So now that's the overview. Go ahead and look at some of my videos where I walk through examples for you.